So my concern in this lecture is what are called partial derivatives. And the reason why we're going to be looking at those concerns an issue that I raised at the end of the last lecture. So we have various techniques for dealing with optimization problems, but there's a bit of a drawback to those techniques. The only concern they can only be applied to functions with a single variable. Now, if we look at optimization problems as they'll arise in real-world settings, what we'll be dealing with are multivariable functions. We won't be concerned with finding the value of a single parameter. We will want to find the right settings for a number of parameters. So how do we go about doing that? Well, here's an example case. We have a function of two variables. We can think of plotting or drawing that function using this sort of diagram. We have the values of one parameter, one variable along one axis. Another axis gives the values for the other parameter, and the actual value of the function itself is plotted on this axis. So we have this kind of mesh that we can think of being the outcome of plotting that function. And this raises some questions. The surface that we showed on that slide, this is depicting a function of two variables. Let's call that function f of x, y, or we may sometimes write it in this form here. Some choice of values for the parameters x and y, that choice will maximize the value of the function. So how do we find that value? Can we use a similar method to the techniques we used when we were analyzing a function of a single variable, those that I described over the last two lectures? What if we have more than two variables? What if we have three or four, or in general some number of n variables involved? Can we use these techniques in that case? And here are some of the problems that arise. When we looked at the notion of maximum value, minimal value, the way in which we justified our derivation of those, the way in which we supported our derivation, what we did was we considered the behavior of gradients of lines touching a point on the curve that was plotted. And we could justify our notion of minimum and maximum. We could justify our formal definition of critical point as somewhere where the gradient became zero, because the way in which the gradient changed, very small changes in the gradient as we moved along the horizontal axis, those would result in the gradient increasing, becoming zero, decreasing, or decreasing, becoming zero, and increasing, corresponding to maximum and minimum values. Now, when we move to two or more variables, we can't safely use that analogy of a line, the gradient of a line as it moves along a curve. So we have to adopt some different approach. So let's take an example function of two variables, this function here. And what we're trying to find, what we want to know are what are the values of x and of y which will maximize the result of this function. In fact, we might even want to discover in the first place, are there any such values which would maximize or indeed minimize the particular function? And the main concern we'd have is if there are maximizing, minimizing values, how do we go about finding those values? So the approach we take to that problem is we use this concept of what I'm going to be calling the partial derivative of a function. So, what is this notion of a partial derivative? Let's go back to our initial function that we're considering. We're trying to find values of this parameter, value of this parameter, which will maximize this function. Now, suppose our y value was a constant. Then we would know how to find the maximizing value for the other parameter. Those are the techniques that we saw in the previous lecture. And in the same way, if it was the case that the x parameter was fixed, we would know how to find the value of y, the other parameter, which would maximize our function. But what we want to do is we want to do those simultaneously. Find a value of x and a value of y, which when we apply them as the inputs to our function, this will give us a maximal point, a maximizing value. So, well, let's suppose that our second parameter is actually fixed, and we find the right value of the first parameter. And let's suppose that our first parameter is fixed, and we find the right value of the second parameter. Then what we have from these two conditions here are a pair of simultaneous equations which we have to solve. So how do we derive that system of equations? Again, let's go back to our initial function. Let's assume that the second parameter is fixed. And now what do we do to find the correct value of the first parameter? Well, we differentiate the function which we are interested in with respect to that first parameter. So what we mean, we differentiate our function, but as if the second parameter y was a constant. And that gives us this. So we use this notation to define that particular function, that particular derivative, and what we find is that is equal to this expression here. Why is that? If we differentiate 3x squared, remembering that y is a constant, we just get 6x, 2 times 3. If we differentiate 2y squared, remembering that we're assuming y is fixed, this term disappears. If we differentiate x times y, with y assumed to be a constant, then we just get y coming out. We do the same thing with the second parameter. We assume the first parameter is fixed, and we differentiate our function under that assumption. Then we get, now the notation we're using is our function with a subscript the second parameter, and this time we get this as our outcome. Why is that? If our first parameter is fixed, this term disappears. We differentiate the second term, we get 2 times 2, which is 4, multiplied by y. We differentiate this term, assuming that our first parameter is fixed, and again it's with respect to y, so we just get this term here. And now what we have to do is identify the values of x and y which make this equal to 0 and at the same time make this equal to 0. In other words, we have our two simultaneous equations. So I'm going to introduce a bit of notation before continuing. If we have a function of two variables, then if we are holding the second parameter constant and finding the derivative with respect to the first variable, we use this notation, and this is called the first partial derivative of our function with respect to x. Similarly, if we are holding our first variable constant, here we held the y constant differentiated with respect to x. In the second case, we hold the x constant and differentiate with respect to y, and this function is called the first partial derivative of our function with respect to y. There are other notations which are used. We have this so-called partial symbol, and much as we wrote dy by dx before, we write partial z by partial x, partial z by partial y. In general, if we have a function which depends on n variables, we'll use this style of notation for our partial derivatives. So let's go on. Let's go back to our original function. We've seen that the first partial derivative with respect to x is this function. Its first partial derivative with respect to y is this function. So we have our two simultaneous equations. When is this equal to 0? When is this equal to 0 for values of x and y? And we find out that the only solution, the only values of x and y which satisfy this set of equations, that is when x is equal to 0 and y is equal to 0. So this function, this is a maximum value at the point when x equals 0 and y equals 0. How do we know that that point is actually a maximum? Well, when we asked that question with our first derivatives, so with the other single variable differentiation, what we used was a method called the second derivative test. So we need some kind of analog of that. We have what is called the second derivative test with two variables. And this is quite complicated. It's actually similar sort of structure to what we had earlier, but it's rather more involved. So one of the problems, when we had a single variable function, we had a single first derivative and a single second derivative, and so on. When we have two variables, we have two first partial derivatives, and we have four second partial derivatives. In general, if we have a number of variables, if we have n variables, we have n squared second order partial derivatives. And so the first thing we have to think about in formulating a second derivative test is, how do we combine these together? So we have our four forms, which I will use this notation to describe. In general, we will have the partial notation like this. What we want to know, how do we combine these? So the interpretation of this notation, f sub xx, that means the partial derivative of the partial derivative with respect to x, again with respect to x. So we take this function and we find its partial derivative with respect to our variable x. In the same way, this notation means we take this function, the partial derivative of f with respect to y, and we differentiate that function but with respect to x. Same way for this and for this. And so again, if we go back to our original function, what do we find? This function is a constant minus 6. This function, constant minus 1, as is this function, and our final second order partial derivative is a constant minus 4. In general, what we will find is that the order we use to form partial derivatives isn't important. This function, irrespective of what f is, will always be the same as this function. The order, whether we do y, then x, or x, then y, is unimportant. The functions are identical. So how do we use the second derivative test? Well, first of all, there's quite a complicated precondition that has to be satisfied. If we look at this function described on the slide, applied to the critical point we're trying to analyze, then that function has to be positive. And then we find, very much as we had before, if applying the second order partial derivative, which uses x and then x again, if we apply that function to the critical point and the result is positive, then the critical point is a minimum. If we apply that function to the critical point and the outcome is negative, then that critical point is a maximum. And again, as we had before with the second derivative test, if we apply that function to the critical point and the result is 0, then once again we can't make any conclusion. Now there's quite a sophisticated extension of the second derivative test with an arbitrary number of variables. This is a structure which is called the Hessian. It's described in the textbook. And if you want to see a much more detailed analysis of a two-variable case, there's one described in the textbook itself. So this concludes our review of differential calculus. What we're going to move on to next is the notion of integral calculus, and that's something I'll be doing in the next lecture.